I was thinking recently about something like a simple number line. We intuitively assume that if a set of points exists, it has to take up space. It has to have some length.
Mm.
But what if I told you that there are these infinite collections of numbers that exist, yet they occupy literally zero length?
Well, that's it. That's the whole counterintuitive idea we're diving into today. The null set.
The null set.
Yeah. In mathematical analysis, specifically with what's called the Lebesgue measure, a null set is just a measurable set of real numbers that has a measure of 0.
Okay, so wait. That sounds like we're just talking about the empty set.
Yeah.
I mean, if it has no length, doesn't that mean it has no elements?
That's the most common misconception. And it's a great question. The empty set is definitely null, sure. But the null sets we really care about in analysis are, well, they're often profoundly non-empty.
So how does that work?
It boils down to the technical definition. A null set is any set you can cover with a countable collection of intervals where the total length of all those little intervals can be made as small as you want.
Arbitrarily small.
Arbitrarily small. Less than any tiny positive number you can name. We call it epsilon. It's like you can catch all the points in a net that you can shrink and shrink until it's effectively gone.
I see. So if the net can always be made smaller, the thing inside must have zero content.
Precisely. And what's amazing is where this applies. The easiest examples are countable sets. Any finite set, or even a countably infinite set, like, say, the natural numbers, that's a null set.
This brings us to the famous one, the one I always get stuck on.
Hmm.
The rational numbers. They're countable, so they're a null set.
Right.
But they're also dense. You can find a rational number between any two real numbers. It just feels like a logical contradiction. How can they be everywhere but take up no space?
Because density is about distribution, not content. Think of it like an infinitely fine dusting of powder. It's everywhere, but the individual grains are just points.
Because you can put a tiny, tiny interval around each one.
And because you can count them, you can make those intervals so tiny that their total length just adds up to 0.
Okay, but the real mind bender, the one that challenges that whole countability argument, is the Cantor set.
Yes.
It's an uncountable set. It has way more points than the rationals, but it's still a null set.
It's the ultimate example. It's this beautiful construction where you start with the line from 0 to 1, and you just keep removing the open middle third of every piece that's left.
So at every step, the total length gets multiplied by 2/3.
Exactly. And if you do that infinitely many times, the length approaches 0. It proves that just because something exists, that doesn't guarantee it takes up any space.
And this holds up in higher dimensions too, like for areas and volumes.
Absolutely. It generalizes beautifully. Any set in, say, a 2D plane whose dimension is smaller than 2 has 0 area. So a line or a circle drawn on a piece of paper technically takes up 0 space.
Wow.
We even see it in things like Sard's lemma, which basically says the set of certain special values from a smooth function has to have measure 0.
So these properties they're really fundamental.
They are. Null sets form what's called a sideal, which in simple terms means they're very well behaved. If you lump a bunch of null sets together, you still get a null set. They don't suddenly create something with positive measure.
And that stability lets us, ignore them.
Sort of, yeah. It leads to this crucial idea in measure theory of something being true almost everywhere.
Almost everywhere, meaning it's true for every point except on one of these negligible null sets.
You got it. Which is so practical because in the real world, you always have noise and outliers in your data.
And being able to build tools that can handle that is key. Speaking of powerful tools, if you're tackling complex data problems like with AI training or automation, and you need help figuring out where agents can make the most impact, you should check out embersilk.com. They really specialize in turning this kind of complex theory into real-world advantages.
And that ability to ignore null sets is really the foundation of the modern Lebesgue integral. In that system, two functions are considered equivalent if they only differ on a null set.
Because their integrals will be the same. So it's like a formal way of being a little tolerant of imperfections, right?
Yeah.
Without breaking the whole mathematical structure.
That's a great way to put it. It formalizes tolerance, and that rigor extends into even higher math, like Harnull sets in Banach spaces, which is all about finding sets that stay null even when you shift them around.
So where does this all lead? What's the next frontier for nothingness?
Well, the most profound thing, I think, is that even within these sets that take up no space, like the Cantor set, you can find hidden structures that are so complex, they challenge our standard ways of measuring things.
Really?
Yeah, it shows us that even in what we define as nothing, There's this incredible complex universe that's constantly pushing mathematics to become more complete, more powerful.
That's an inspiring thought. Our ability to define nothing is actually strengthening our ability to understand everything.
Always.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.